In Lesson 8.10, Taylor and Maclaurin Series, we're going to expand upon the idea of the Taylor and Maclaurin polynomials that we learned a few lessons back. If you recall, those polynomials were simply approximations. The more terms we put onto the polynomial, the better approximation it was, but it was never perfect. And that's why we had to deal with that Lagrange error bound that you probably recall. So, what we're going to do is find a better and more efficient way to write those polynomial approximations. See, those polynomials are actually just a few terms in a series written out. So what we're going to do in lesson 8.10 is find the definition for that particular Taylor or Maclaurin series, of which the polynomial was just an approximation. You'll see that it's not that difficult of a thing to do and extremely useful, because with the Taylor-Maclaurin series, we don't need to deal with approximations, we don't need to deal with remainders, or any of that stuff. So, before we begin looking at Taylor and Maclaurin series, perhaps it would behoove us to review real quickly lesson 8.7, where we learned about Taylor and Maclaurin polynomials. So, real quickly, here is our review of Maclaurin polynomials, Taylor polynomials, and the Lagrange error bound. Let's go ahead and focus first on our Maclaurin polynomials. You'll remember that each one of these terms of this polynomial has a coefficient followed by x to the power of whatever term that we're in. Notice for every single one of these terms, the denominator, the exponent, they're both the same. In the first term, there's 0 factorial on the bottom, x to the 0 power, which really we don't usually write, but I'm just putting it there for posterity's sake. There it is. In the second term, it's 1 factorial on the bottom, and the exponent is to the first power. Really, that is the first term of the series, if we consider the first one to be the 0th term. So think about it that way, actually. The 0th term, the first term, the second term, and so on. And when we get all the way to the end over there, you see that we have n factorial on the bottom and x raised to the n power. Remember, that is really just an approximation, but let's go ahead and move down a little bit. And here we are. Let's take a look at this Taylor polynomial. Taylor polynomial looks very much the same. You'll recall, hopefully, that the only difference between the Maclaurin and Taylor polynomials is where the polynomial is centered. And that's why here in the Taylor polynomial, each term has an x minus c to some power. Other than that, there's really no difference. You will recall, however, that if we move down one more time, and there we are, the Lagrange error bound. You probably recall not liking this too much. It's not most people's favorite thing to work with, but it is extremely important because the Taylor-Maclaurin polynomials are just approximations, and this error bound tells us how approximate they are. So that's just a quick review. What we're going to do here in lesson 8.10 is take that entire polynomial and condense it down to one series definition. Now, if we were to write out that series, we would get the polynomials, but the series won't need an error bound. It's not an approximation. It will be exact, well, as the limit of n approaches infinity anyway. So, anyway, all that being said, let's go ahead and define the Taylor and Maclaurin series before we move on. I'll show you a couple guidelines for finding those series, and then we'll do a few examples. Now that we've had the opportunity to go back and take a look at the Taylor and Maclaurin polynomial approximations, here is our definition of the Taylor and Maclaurin series. Remember, this is just the condensation of that long polynomial into one series definition. So, if the function has derivatives of all orders at x equals c, that is the center of our function here, then the Taylor series we're going to define as the sum from n equals 0 to infinity of f, the nth derivative of f, evaluated at c over n factorial times, our x term, x minus c, to the nth power. So that should look very, very, very familiar to you. That is, in fact, each one of the terms of our Taylor series. Now, based on that, how do we find a Maclaurin series You should be okay with that. That's just going to happen when we have a Taylor series that's centered at c equals 0. That simplifies a few things because it enables us to just put 0 in here and to get rid of this if we're dealing with a Maclaurin series. But, of course, it's important for us to know both the Taylor and Maclaurin variants of what we're doing here. So, all this being said, let me show you a few guidelines for doing a Taylor series, and then we'll get into our examples. So long as you're good at looking for patterns, building your Taylor series is not going to be particularly difficult. However, there are a couple things you should look out for. So, if I'm going to show you guidelines for building a Taylor series, our first step would be to build the Taylor polynomial. Again, that goes back to lesson 8.7, and it's what we were discussing at the beginning of this lesson. Again, that's where you do the derivative a number of times. I would suggest at least 3 or 4 times. Plug in the value c for each one of those, and then you can build your polynomial. Now, once you've done that, I'm going to suggest that you leave any factorials and exponents alone. Leave factorials and exponents alone. And in doing that, you should look for a pattern. See if there's any common ratio between the constants in each term, or anything at all, really. If you do not see a pattern, then go ahead and expand the factorials and the exponents. This might take a little bit of work, but you'll see that sometimes you need to do it and sometimes you don't. So if we expand the factorials and exponents and now look for a pattern, between one of these steps, between step 2 or step 3, you should find your pattern. And once you find your pattern, then you can go ahead and build your series as such. It'll go from 0 to infinity, and it will always involve some aspect of the derivative of f at c. There will always be, almost always, some aspect of n factorial in the denominator, and then, of course, x minus c to some power or another. So there's a simple 3-step system, really, which could turn into 4 if you don't notice a pattern at first. And this is the procedure that we're going to follow for each one of our examples, starting with this one now. The first Taylor series that we're going to build in this lesson involves the function f of x equals sine of x. This, most assuredly, is a Taylor series that you should have memorized within the next few days, to be honest. At the end of this video, I'm going to show you a list of particular functions that you should just know the Taylor series representation of. And sine of x is one of those functions. But for now, let's go ahead and work this out. The first thing we want to do is build a Taylor polynomial for this. And this is a Taylor polynomial because we're not centered at 0. Of course, we already have that f of x equals the sine of x. We'll come back through later and evaluate that at c. If we do the derivative of sine of x, of course, that will give us the cosine of x. If we do the second derivative, we'll return back to sine of x, but it will be negative this time around. The third derivative will be negative cosine of x, and I'm actually going to stop there because I think with this polynomial, we'll be able to see the pattern pretty well. So, if we evaluate this at f of c, remember that c is pi over 4, so sine of pi over 4, that's of course the square root of 2 over 2. The first derivative evaluated at c is the same thing, square root of 2 over 2. Are they all going to be that way? Well, if we take a look at our second derivative, we see, no, they're not all going to be that way. This one has a negative, as does the third derivative. And these should be evaluated at c rather than x. But these are both negative. So this is interesting. It's not quite an alternating series because it's not positive, negative, positive, negative. But we do have this weird pattern where we'll have 2 positives and then 2 negatives, and if you keep going, you'll see that we'll have 2 more positives, 2 negatives. So in this example, I'll show you a way that we can play with the exponent, or play with a negative 1 power, so that there are 2 positives, 2 negatives, 2 positives, 2 negatives. You'll see what I mean in just a moment here. But if we go ahead and build this polynomial here, this is going to be a third degree polynomial. Taylor polynomial for x. So if we do that, of course our first term is going to be square root of 2 divided by 2 times 0 factorial. Don't forget the factorial as you're building these terms. And we'll have x minus pi over 4 to the 0 power. Now, of course, that whole thing can be simplified, but just for the sake of looking for a pattern, I'll leave it written out like this. So our second term, again, is going to have square root of 2 in the numerator, 2 in the denominator, but this time there'll be a 1 factorial and x minus pi over 4 to the first power. All right, well, let me keep up with this. Notice that the next term will be minus, and if you look down here, you'll see why. The next two terms, in fact, are both negative. So it'll be square root of 2 over 2 times 2 factorial. And of course, I could expand that out and simplify, but I'm looking for a pattern, so I'll leave it alone for now. And my third term here is going to say square root of 2 over 2 times 3 factorial. And this will be x minus pi over 4 to the third power. Alright, so looking at this polynomial here, do you notice any patterns at all? Any at all? Hopefully you notice that each one has a square root of 2 on top and a 2 on the bottom. That seems perfectly relevant. Also, we have n factorial in the denominator for each one. In the 0th term, 0 factorial. The first term, 1 factorial, and so on and so on. So, all kinds of interesting things here. The only big issue that I have, as I referenced before, is that we have 2 positive terms, and then 2 negative terms, and then 2 positive terms. So I'll show you how to handle that in just a moment. But if we want to write this as a series, of course, n will start at 0 and go to infinity. And in this series, each term will have a square root of 2 in the numerator, and each term in the series will have a 2 in the denominator. What would be the next easiest part to pick out? If you ask me, it would be the n factorial that keeps showing up in the denominator. Now be very careful. This does not say quantity 2n factorial. This says 2 times the quantity n factorial. It's not much of a quantity at all, but if you want that multiplying dot there, that's fine. Go for it. Now, how am I going to handle this negative 1 that goes 2 by 2 by 2? I'm just going to go ahead and give this to you right here. I'll leave it to you to verify. But if I go n times the quantity n minus 1, and then divide that by 2, I think you'll see that instead of alternating does a double alternate. You can go ahead and verify that for yourself. But remember that n times n minus 1 minus, all over 2 if you need that. Now, of course, it might look kind of iffy that we're going to have a negative when we plug 0 in. But this 0 here will take care of that situation. When we plug 1 in, that'll take care of that, and it'll go on and on. Now, there's really only one thing I'm forgetting here in this series, and that is going to be my x minus c raised to the nth power. So, it's not a pretty series. It's certainly not pretty, but it does take care of everything. Each term will have a square root of 2. Each term will have a 2 in the denominator, in that n factorial. Here's the x term, which seems pretty obvious, and then this will cause my negative to go 2 by 2 by 2. So, that's how you do a Taylor series. It all starts with that Taylor polynomial from lesson 8.7. Write that out, look for a pattern, and then you're good to go. Notice in this one I did not have to expand the factorials. I did not have to expand any powers. It was just laid out for me quite nicely. Well, let's take a look at one more example dealing with a Taylor series, and then we'll move into a couple Maclaurin series. Well, guys, it looks like I lied to you. Even though it says this is a Taylor series, you'll notice that this particular Taylor series is centered at c equals 0. I'll hesitate to say this is a Maclaurin series, but a Taylor series centered at 0, you can draw your own conclusions about that one. Alright, regardless of where this series is going to be centered, we're still going to attack it the same way. We're going to start by finding the Taylor polynomial centered at 0, and then based on that we'll look for patterns and see if we can find the Taylor series. This is a natural log function. I referenced in the first example that in a few days you should have a bunch of these Taylor series memorized, and good news. the natural log is one of those that you should have memorized. So, again, at the end of this lesson, I'll show you a list of ones that you should know. And at that point, I'll invite you to come back, try this example again with your newfound information, and see that it's actually a lot easier that way. Regardless of that, let's go ahead and start writing out the Taylor polynomial. Of course, we know what f of x is. That was given to us at the very beginning, and I'll evaluate that at 0 in just a moment. If I do the first derivative of this, that's not entirely difficult. It's just going to be 2x divided by x plus 1, or x squared plus 1, rather. And again, I'll evaluate that at 0 here in a moment. For the second derivative, it does start to get a little hairy here. Clearly, we're going to have to use the quotient rule. I can promise you it's not going to be pretty, but luckily, I did work these out earlier. So, the second derivative of this one is simply going to be negative 2x squared plus 2 divided by the quantity x squared plus 1 squared. Alright? Could you have found that out yourself? I'm certainly hoping so. It's not entirely difficult, but you don't want to waste time on that right now. I'll just promise you it's true. So the third derivative, it's going to get even nastier still. This is going to be 4x cubed minus 12x divided by my bottom quantity cubed. So it's just getting uglier and uglier. The fourth derivative, I hesitate to even put this one up because it's just terrible. So I won't put it up. I'll leave that one to you as an exercise. It ain't pretty, but, it is what it is. So let's go through and start evaluating all of these at 0. If I evaluate this at 0, it'll be the natural log of 1. Well, that's 0. If I evaluate the first derivative at 0, I'll have a 0 in the numerator and 1 in the denominator, 0 over 1. Alright, no problem there. The second derivative evaluated at 0. Here you can see that that's going to cancel out, but I will have 2 over 1, and 2 over 1 is just 2. Wow, these derivatives kind of sucked, but evaluating them at 0 is not too bad. So the third derivative at 0 is 0. The fourth derivative, although I didn't show you what the fourth derivative was, what I will promise you is that evaluated at 0, it would yield negative 12. Now, the fifth derivative, which again, I've gone ahead and figured out, and you can do the same, but that'll give us 0. And let me do the sixth derivative just because I feel like that would be a lot of fun. Evaluating that at 0 would give us 240. And now you're probably wondering, wow, I wonder what that derivative was to give us a number like 240, and I certainly invite you to work it out. I've already done it, so I'm good with all that. Fun and exciting, yes. Willing to do it all over again, not completely. So, anyway, these are the values that we come up with. If we want to make our Taylor polynomial, and again, I can make this a 6th degree polynomial. I know so much information about it already. So, what is this going to look like? Well, our 0th term will be 0. Our first term will be 0 again. So our first term is that we actually see is going to be 2. I need to divide that, of course, by 2 factorial. And then I'll do x minus 0 to the second power. I'm not actually going to write x minus 0, of course, but you see that that is the case. So our next term will be 12. 12 will be my coefficient right here, and remember the negative, so it's minus. I'll divide this by 4 factorial, and this will be x to the 4th. And now for my 6th term, this is going back to positive again. I'll have plus 240 divided by 6 factorial, x to the 6th. So, just looking at that, do you see any patterns? I mean, certainly the denominator, we have 2 factorial, and then 4 factorial, and then 6 factorial. Okay, that's something. And the exponent is going to be 2, 4, and 6. That's all fine and dandy, but we look at the numerator. We have 2, we have 12, we have 240. I have no idea. I have no idea. And then, on top of it all, I have positive, negative, positive, so I'm going to have an alternating series. At first glance, this just looks like a giant mess, and I'm not really sure where to go with it. So, let me go ahead and expand these factorials and see what happens. If I do expand this, this will be 2 over 2. 2 over 2. This is really just going to be x squared. that's something. Now if I come over here, this 4 factorial, if you multiply this out, 4 factorial is actually going to give us 24 in the denominator, and 12 over 24, that's just going to be 1/2. And let me do that one more time here. If I do 6 factorial, that's going to come out to be 720, which interestingly, this would be plus 1/3 x to the 6th power. Now I'm starting to notice a pattern, and I'm hoping you notice it too. If I write this as 1 over 1, notice that the numerator is staying 1, the denominator is increasing by 1 in each term. It is an alternating series, so I have to deal with that, and then my exponent here. So let's see what my Taylor series might look like here. Of course, I'll do the sum from n equals 0 to infinity. Each term is just going to have a 1 on the top. So I'm not going to bother with that too much, but let me deal with the alternating nature of the terms. I'll have -1, and I want it to start as a positive, turn to a negative. Alright, so if I start it as a positive, let me start it with n, because n will start at 0. Alright, so that'll work. In the denominator, well, if n is 0 for my 0th term, I need to add 1 to get to this. And my denominator will just say n plus 1. Great, so I have the alternating series part of this. I have the denominator part. The numerator part is just a bunch of 1s. And the last thing I need to deal with is just x. Now x, if you notice, the exponent is going up by 2 on each term. So that will keep it going up by 2 on each term. However, for my 0th term, I need the exponent to be 2. If I plug 0 in here, I get x to the 0. If I just add 2 to that, that should do it. So here is my Taylor series. You can see that it is a little bit tedious. I won't hold back on that. But it's certainly doable as long as you start by writing out your Taylor polynomial. Of course, at the end of the lesson, what I'll say is so long as you have certain one memorized, it'll be a lot easier. And you'll see how this natural log one connects when we get there. Well, all that being said, let's take a look at a couple actual Maclaurin polynomials, stated Maclaurin polynomials. And we'll try to find the Maclaurin series based off of those. And these will be fun and exciting. So I hope you find these next two examples to be relatively easy. We are going to find the Maclaurin series for the given function. It's just like finding the Taylor series, except we don't have to deal with c, so that's pretty nice. Just like before, let's begin by writing out our Maclaurin polynomial. The way we'll do that is just differentiate f of x a number of times. I'll start with my original f of x, and then I'll just go ahead and do a few derivatives. E to the x is another one of those functions that you really do need to memorize the series for. It would make this problem a lot easier in that you wouldn't have to write out the polynomial. And after all, writing out the polynomial is the hardest part to these things, so it could save you a little bit of time. Now what I'm going to do is I'm going to go up to the fourth derivative here, and I'm going to stop at this point. So I have these as my first 4 derivatives. If I evaluate each one at 0, because remember, Maclaurin says c equals 0. So f of 0, that's easy, that's e to the 0 power. F prime of 0 is going to be -3, and in fact each of these is just going to be the coefficient in front of the e term. So this isn't too bad here. Easy to work out, not hard to execute, and it looks kind of like that. So there are the coefficients to the terms of my Maclaurin series. Let's go ahead and write out my Maclaurin series, and I will take this out to the 4th term. Now my 0th term will just be 1 over 0 factorial x to the 0 power. Now remember, 0 factorial is defined as 1, so it's okay to have that in the denominator. My next term will be 3 over 1 factorial x to the 1st. And I'll continue this on. I'll have 9 over 2 factorial x squared. And notice that I am alternating here. This is clearly going to be an alternating series, so I will certainly have to deal with that. But hopefully that should not be particularly difficult to deal with. I'll just have a -1 term. So here is my Maclaurin polynomial. Pretty exciting. And hopefully you see the pattern here. The denominator is just increasing by 1 factorial each time. My numerator, they're just powers of 3. Just powers of 3, no big deal. It is alternating, so I'll need to deal with that. And then, of course, x just increases by 1 for each term. So, what will this Maclaurin series look like? It'll be the sum from n equals 0 to infinity. I do have to deal with this alternating series issue. So there we go. That takes care of the plus, minus, plus, minus, plus, minus. And notice that when I plug in 0, it is positive. So it is starting correctly. That's very important. Then it looks like I'm going to have 3 to the n power. For my first term, n is 0. And if I plug 3 to the 0 power, certainly that does give me 1. So that works out for my first term. In the denominator, looks like I'm just going to have n factorial. That's clear. There's my 0, 1, 2, 3, 4, and so on. And then I will just have x to the nth power. So that really is my entire Maclaurin series. Now, you could simplify this if you like. And if it's a multiple choice question, you want to be on the lookout because either one of these could be accurate. I could combine my alternating series into my 3 and write it like this. So this is another way that this series could be written. And then finally, I want to show you one last way that this series could be written. These series can be written many, many ways. Notice that there's a bunch of things that are all to the n power. In a sense, I can just smash them all together and end up with this as my Maclaurin series. This, quite honestly, is probably the preferable approach to it, just in that there's fewer number of terms and it's a lot easier to look at. But understand that any one of these 3 is going to be correct. In our last example that we're going to do here, I'm going to leave it up to you to go ahead and differentiate this function a number of times and evaluate it each time at 0. If you pause this video, take a few minutes, work that out, and let's see if you get the same polynomial that I do. So, when you're ready, come on back. So, hopefully you've given this a shot, and hopefully what you've gotten for your polynomial, and what I'm going to do is I'm going to go up to the 6th iteration of this polynomial, but hopefully you've gotten something along the lines of 1 over 0 factorial x to the 0, followed by negative 16 over 2 factorial x squared. That'll continue on. We'll go plus 256 over 4 factorial x to the 4th. And finally, 4096. This thing got big real quickly. And that'll be over 6 factorial x to the 6th. If you did not get that as your polynomial, go back, check your work. This is correct. All right. However, looking at this, do you see any patterns? That's the big question. Do you see any patterns? Remember, of course, that this is the 0th term. This is the first term. This is the second term. And this is the third term as far as what n equals on each of these. N equals 0, 1, 2, 3. Do you see the pattern? Well, certainly the denominator looks like it's going to be n doubled and then factorial. So if we take that into account, okay, we'll do the sum from n equals 0 to infinity. And again, we have on the bottom twice of n factorial. All right, notice that this is different than just 2n factorial. This is quantity 2n factorial. So be very careful on that. Now, in the numerator, the first thing I want you to notice is, again, we do have an alternating series. So let me go ahead and address that. It starts positive. So I'll start with n, which is 0. All right. And then it looks like what we have here looks like powers of 16. All right. So if we handle it this way, we will go 16 to the nth power. 16 to the 0 is 1. 16 to the first is 16. 16 squared is 256. And you can check 16 cubed and see that that is correct. So there's going to be our big coefficient here. And then x, it looks like, is just going to be raised to the 2n power for each of these. Now, we could, again, write this a little bit differently. If you think of 16 to the nth power, if you think of that as 4 to the 2n power, then there's something we can do with this and this, the 4 to the 2n and x to the 2n. So let me just show you this because it could show up on a multiple choice question. And if you don't recognize it, it will get you. So if we call this, instead of 4 to the 2n and x to the 2n, let's call it quantity 4x to the 2n power. And then, of course, we still have the 2n factorial in the denominator. So either one of these two variants will work, although this one right here might show up more often. So, all this being said, I've been preaching throughout this entire lesson that at the end, I would show you a list of functions whose series you should memorize. They come up often enough, and they're common enough that really you should just be able to, boom, and find their Taylor or Maclaurin series. So, let me go ahead and show you those, and of course, I'm going to invite you to try them on your own to prove that they're correct, but here they are now. So, I've been promising you a list of functions whose Taylor series you should have memorized. And here's that list, right down here. You should know all of these. Now, I will admit to you that the first three are certainly the most important of the five, but knowing the fourth and fifth one could prove to be useful over the course of time. So, as you're doing your homework, understand that if you know these simple functions right here, if you have their Taylor series memorized, you've just made your work a lot easier to deal with. In fact, at this moment, I would even recommend that you go back and try some of the problems on these notes that we just finished, using this information right down here. It could only help you to understand what's going on and show you that it actually does make things a little bit easier. You, of course, can generate any of these. I'm just saying that memorizing them would be a time-saving measure, and a big one at that. So, write these functions down here, write down their series, and understand that to make a Taylor series, simply start with writing the Taylor polynomial. It all starts there. Also remember that a Taylor series is just a quick way to approximate, or actually if it's a series as n goes to infinity, to calculate the value of any f of c. It doesn't seem like it makes things easier, but if you were a calculator, or if you were a computer, or if you had to do a multitude of these problems, finding the sign of x for each value would certainly take a lot longer than some series as we plug in that value for x. So remember, that's the whole idea, is simply rewriting a non-elementary function as an elementary series. So consider that a little bit as you work throughout your homework, and good luck.